All right, let's talk about analytical techniques. Once again, these are your objectives. I'll let you go ahead and read through. So techniques. So there are four major disciplines. We have spectrophotometry, atomic absorption, and mass spectrophotometry. Luminescence, which is fluorescence and nephelometry. Electroanalytical, which is electrophoresis, and chromatography. There is some new technologies such as miniaturization, like point-of-care testing devices. So spectrophotometry. The purpose of this is to measure electromagnetic radiation or light and how it interacts with the substances or solutions. So the function is that it will determine light intensity and how much light is absorbed or transmitted by a sample. So how does it work? It works by having light pass through a sample, and it can be absorbed, transmitted, or reflected. The instruments are designed to measure the absorption, which is the most common, or the transmission. Key features of this is it uses filters, prisms, and gratings to help isolate specific wavelengths and help to ensure accuracy and specificity in measurements. So Beer's law for the spectrophotometry. The definition of Beer's law is it describes the relationship between the concentration of a solution and its light absorption. So basically, the amount of light absorbed by a solution is directly proportional to the concentration of the absorbing substance, inversely proportional to the logarithm of the transmitted light. So this is the formula. It is A equals epsilon times B times C, where A equals absorbance, epsilon equals molar absorptivity, B is the path length in centimeters, and C is the concentration in moles per liter. You do not need to know how to calculate this, but just know that that is Beer's law. We also have absorbance, A, and percent transmittance, and they are related. So A equals 2 minus the log of the percent of the transmittance. So basically the process overview is you have a beam of monochromatic light that passes through the solution. Some of the light is then absorbed, the rest is transmitted, and then it measures how much light is absorbed, and that gives the information about the solution's concentration. So Beer's law, practical applications, we have light interaction. The instruments will detect the amount of light based on the absorption and transmission. If no light is absorbed, then the percent transmission is 100% and the absorbance is 0. So we will use a blank solution to set that baseline to get that 100% percent transmission or absorbance. So this will account for any absorbance due to the solvent or cuvette as well. Why this matters. So the difference in light transmission between the blank and the sample reflects the amount of analyte that you're looking for, how much is actually present. This will help to enable quantification of substances in the solution using those absorbance values. So make sure you just kind of remember the absorbance formula, which is that absorbance, which is A, equals 2 minus the log of the percent transmittance. The core principle of Beer's law, so once again, the amount of light absorbed by the solution is directly proportional to the concentration of the absorbing substance. It works by a monochromatic light, which is passed through the solution. Some light is absorbed and the rest is transmitted, like mentioned. Instruments measure either the absorbance or transmittance. So there's another calculation you can use where it says Cu, which is the unknown concentration, times the AU times the CS divided by AS. So AU is the absorbance of unknown, CS is the concentration of the standard, and AS is the absorbance of the standard as well. Once again, you shouldn't need to know how to calculate this, but I would know what this is for. Some factors that can affect absorbance, concentration, wavelength of light, the type of molecule or ion, the pH, and temperature. For calibration, it will be a plot absorbance versus concentration to create a calibration curve. We're going to use the curve to determine unknown concentrations from their absorbance values. So spectrophotometer. This measures light that is transmitted through a solution to determine the concentration of an analyte. So based on Beer's law, the basic components, or that's based on Beer's law, sorry. The basic components of a spectrophotometer is you have a light source, and that emits the radiation or the light. The tungsten iodide is used for the visible and near infrared light. We have a mercury arc and a lamp, which is used for the UV range. A monochromator isolates specific wavelength of light and uses prisms and filters and gratings. Then we also have a cuvette, which is the sample holder that holds the solution. It must be transparent at the measurement wavelength. That way it can't interfere with the detection of it. And then we have a detector, which measures transmitted or absorbed light intensity. And then we have a readout device, which displays results, which is the absorbance or the percent transmitted. So how this works, light is emitted and passed through the monochromator to isolate one wavelength. This light passes through the sample solution in a cuvette. Some light is absorbed by the analyte, remaining is transmitted. The detector measures light intensity and sends data to the readout. And then the absorbance is then calculated and used to determine the concentration by either Beer's law equation or that calibration curve. So monochromators, which is part of the spectrophotometer, the purpose of that is to isolate a specific wavelength of light from the broad spectrum, which is emitted by the light source. Types of monochromators are, we have a glass filter, which is the least expensive. It allows a wide band of light through, but it's not really precise. And then we have interference filters, which transmit multiples of desired wavelength. Need accessory filters to block unwanted wavelength. The prisms, which are a light beam, is refracted through the prism. Rotation allows selection of desired wavelength via the exit slit. The diffraction gratings, which are the most common ones that you're going to find today, they are made of parallel grooves. The light is bent or diffracted to help separate the wavelengths. All right, so sample cell and photodetectors in the spectrophotometer. The sample cell or the cuvette holds the solution that's being analyzed. It can be round or square in shape and must have a consistent absorption for accuracy. Often they are etched to mark a specific position for consistent placement. The material is going to depend on the wavelength. So glass is going to be used for visible light range, and then we'll use quartz for UV range since glass actually absorbs UV. Photodetectors will convert transmitted light into electrical signals. So the different types, we have a photocell, which is the least expensive. It generates its own electromotive force. There's no external power that's needed. And we also have a phototube, which does require an external voltage, and it is more sensitive than the photocell. Quality assurance for the spectrophotometer. So you still need to do quality assurance. It checks for the accuracy, precision, and reliability of their measurements. So the wavelength accuracy is going to be confirming the wavelength shown on the dial matches the actual wavelength that is passing through the monochromator. Errors may result in incorrect absorbance readings, and it's verified using standard solutions. Stray light is defined as the light outside the selected wavelength band that reaches the detector. Some causes of this could be there's a scratched optical surface or dust or lint has found its way into the instrument. It leads to baseline errors in nonlinear absorbance at high concentrations. Tests with cutoff filters or specific solutions that absorb light fully at a given wavelength. Linearity verifies that absorbance increases linearly with concentration as predicted by Beer's law. And this helps to ensure that the instrument's response is proportional to analyte concentration, and a straight line calibration curve could be obtained. Fluorometry. So just like with spectrophotometry, light can be transmitted or absorbed, but it does it by excitation and emission. So when a molecule absorbs or excites light, it gains energy and moves to an excited state. The molecule then returns to its ground state, releasing energy as a photon or light, and this is called the emission. For measurement, the fluorometers measure the intensity of emitted light. The filter fluorometers, are used to measure the concentration of molecules that fluoresce or emit light when excited. For the excitation, I cannot speak, source, it emits light at a short wavelength to excite the sample. The fluorescing sample emits light in all directions. The detector is placed at a right angle to the excitation light to avoid detecting the excitation light directly. A secondary filter is used to pass only the longer wavelengths or emission light and block scattered excitation light. The photodetector's electrical output is proportional to the amount of fluorescent energy emitted by the sample. This right angle setup with filters helps to ensure that the detected signal is mainly from the fluorescence emission, which helps to minimize interference from the excitation light. Light sources for the fluorometer is you have a gas discharge lamp. These are the most common. Specifically mercury vapor lamps. They are widely used in filter fluorometers. And then we have monochromators, use filter, prisms, or diffraction gratings to select specific wavelengths. Detectors, you have a photomultiplier tube. They are used as light detectors due to their high sensitivity. So these components enable excitation light production, wavelength selection, and sensitive detection of emitted fluorescence. For the polarization of fluorescence, so light polarization, so light is polarized in a single plane. With the emission behavior, when a fluorophore is excited, it emits polarized light if attached to a large molecule, like immunoglobulin. Small molecules emit depolarized light because they rotate more freely. So applications, we would use this. It's used for detecting therapeutic drugs and drugs of abuse. It works by competition between the analyte and a fluorophore labeled analyte. This technique helps differentiate molecules by their size based on emitted light polarization. Some advantages and disadvantages. So advantages, it has high specificity and sensitivity. It is approximately 1,000 times more sensitive than other methods. But some disadvantages is the fluorescence can be affected if there are changes in the pH, changes in temperature, and if it's contaminated by chemicals. So this method is very powerful, but it requires careful control of the experimental conditions. Electrochemistry. So electrochemical analysis include potentiometry, amperometry, colorimetry. Basic electrochemical cells are your galvanic cells and electrolytic cells. You also have your ISE, or your ion selective electrodes. This is used in potentiometric analysis, and it's measuring electrical potential generated by the activity of the free ions. It is highly sensitive for detecting those individual ions as well. So the pH electrode, some components of that is it has an indicator electrode. It usually is a silver wire that's coated in silver chloride in hydrogen chloride solution. Membrane sensitive only to the hydrogen ions. And then we have the reference electrode. It's a calomel electrode. It's in contact with the metallic mercury in the potassium chloride solution. So how this works is when it's placed in a solution, the hydrogen ions move at the tip of the indicator electrode. This produces a potential difference between the internal solution and the test solution. The potential difference is measured as pH, and then it's displayed by the voltmeter. A stable voltage is generated in the temperature, and the electrolyte concentration will remain constant. Electrical connection between the indicator and reference electrode is maintained by the flow of electrolyte from the reference electrode. The electromotive force, or the EMF, is produced by the reference, and indicator electrodes is measured by millivolts. Electrophoresis. I'm sure you've heard of this one before, but it is the migration of charged solutes in an electrical field. Iontophoresis refers to the migration of small ions. Zone electrophoresis involves charged molecules moving through a support medium. This is used to analyze proteins in serum, urine, spinal fluid. The process involves 5 components. So you would need an electrical power, support medium, buffer, sample, and detecting system. So charged particles will migrate toward the electrode with the opposite charge. The velocity and migration of these particles will depend on the net charge of the particle. the size and shape of the particle, strength of the electrical field, temperature, and supporting medium. So the procedure for electrophoresis is you have a sample is soaked into a hydrated support medium. The support medium is placed in an electrophoresis chamber, which is filled with that buffer solution. And then there is constant voltage that is applied across the chamber for a specified time. Then the support medium is removed from the chamber and placed in a fixative or dried. The separated zones are stained with dye, and the dye uptake is proportional to the concentration of the molecules. Excess dye is then cleared from the support, and the concentration of each zone is measured using a densitometer. The buffer maintains a constant pH and prevents protein denaturization, which is caused by heat that can occur during electrophoresis. And common support media includes the cellulose acetate and agarose gel. The separated protein fractions are stained to determine their locations on the support medium. The densitometry is the most common method used for quantitation of the protein fractions. Quantitation it requires calculating the area under the peak for each fraction on the densitometer output. Osmometry. This is used to measure the concentration of solute particles in a solution. Four physical properties of a solution change with the number of dissolved particles. So you have osmotic pressure, vapor pressure, boiling, and freezing point. Osmometers can measure the osmolality indirectly by measuring one of these colligative properties. The two common methods used are freezing point depression and vapor pressure depression. Freezing point osmometer, so a small tube containing the sample is placed into a chamber which is filled with a cold refrigerant. A thermistor, which is a temperature-sensitive resistor, is immersed directly into the sample to measure that temperature. The wire then stirs the sample continuously to cool it below its freezing point. And then once the sample is below freezing, it is agitated to induce rapid freezing. Alternatively, freezing can be initiated by seeding the solution with small crystals, which helps to prompt ice formation. So the supercooled solution freezes when stirred, and it forms a slushy mixture. The solution then warms up to its freezing point temperature, or cools down, I guess. The decrease in freezing point temperature is directly proportional to the number of dissolved particles or solute present in the sample. This freezing point depression correlates with the osmolality of the solution. And then the instrument is calibrated using known standards to ensure accuracy. Point of care analytical techniques. So requirements for accurate point of care testing is instrument validation, periodic assay calibration, quality control testing, operator training, and proficiency testing. So a common device for this would be like a fingerstick blood glucose monitor. The principle it uses is photometric analysis, and the biochemical reaction, how it works, is glucose reacts with the glucose oxidase, and that produces hydrogen peroxide. The hydrogen peroxide then reacts with the peroxidase, and that produces a colored compound. So the measurement, so the intensity of the color produced, correlates with the glucose concentration in the blood. So basically, it will read the color, and that's how it knows what the glucose level is. Some other techniques for point of care is strip technology. It utilizes paper chromatography. It's lots of times used to measure proteins and cardiac markers. Biosensors, it combines enzymes, antibodies, or nucleic acids with a transducer, and that allows direct measurement of that analyte. And then we also have commercial devices. They are commonly used electrochemical sensors, and they also use optical biosensors can be used to measure at least glucose, electrolytes, and arterial blood gases, or ABGs.